today's notes are about equilibrium, and the idea of this is pretty straightforward. It's just the description of an object that is not accelerating either forward or back. It's not speeding up in a linear fashion, and it's also not spinning faster and faster or slower and slower. It might be spinning, but it doesn't have a net torque on it, and it doesn't have a net force on it either. Okay, so here we have like the simplest example, I guess, in a case where these two kids they're smiling, but they're not really having fun on the seesaw because they're just sitting there. Okay, and so let's do this one together. A couple things we could solve for here are like, for instance, the normal force of like the fulcrum up on the kids, and then we can obviously solve for this distance between the fulcrum and the boy on the right hand side. So when we're looking at this, we could like redraw just the beam, for example. It's a very common thing to do. And so if we're doing that, we can like draw it out. Now, when we've been doing torque problems, we know that like, ooh, wow, that's pretty bad. That we're no longer replacing the object with a dot. We care about where all of these forces are acting. And so I guess we're sort of treating this girl's downward force of her normal force, basically, or her weight, you could think of it as, right there. Okay, and that's a distance from the axis of rotation of the 1.5 they gave us. We have the boy sitting closer, and so if I draw this one, I would try to draw that to scale maybe at 500. We would have, let's say the weight of the beam itself, right? It would have some weight that is probably much less. Okay, so I don't know. For the beam, we don't know that really. Maybe often they'll say it's massless, but we don't really know. So maybe we can't find that right away. And then we would have, let's say, like the normal force, okay, which needs to be much larger. So maybe I should draw a larger arrow here, because the normal force from this triangular support is the only thing that's holding that up. Okay, so then I'm gonna have to draw a very large one, normal force here. Okay, and then the other thing that I can do, I prefer to put R2 in here. Okay, we can also solve for the distance. So if I know that there's no rotation going on here, there's no speeding up, slowing down, looks like zero rotation, then I know that the sum of the torques is 0. So I can, for instance, say that my axis of rotation sure looks like it's right there smack in the middle. And so I'm going to maybe start with that. I'll say net torque is 0. Okay, and so then when I look at all the things that, all the forces, I'm going to say, well, I've got the, this is the girl. So I'd have this force right here would make the seesaw tend to rotate counterclockwise. So that's a positive torque. So then I would do the positive torque from the girl. Okay. Plus the boy, if it was just him on that seesaw, he would cause the whole beam to rotate clockwise. That's a negative torque. Okay. Now the force of the gravity. Oh, I should say, where am I doing all this from? I'm doing it right from the center, the fulcrum. But you could technically, you're allowed to calculate the net torque from anywhere. I mean, you could calculate it from over here where the girl is sitting, even though that's not the axis of rotation, which seems kind of weird. But you're allowed to do that because, really, since the object is not speeding up or slowing down, then we're basically saying, hey, the sum is 0 from anywhere, because otherwise there would be, additional torque. So if it's all canceling, then it's canceling from every perspective. Okay. So I am choosing this perspective, though, because I don't know the weight of this beam. So that's a convenient place to put my, axis, my reference point, because I don't know that force. And so if I put my point there, that's great, because that weight of the beam doesn't produce any torque right at the center. And so great. I have 0 torque from the beam. I also have 0 torque from the normal force, which I hadn't solved for yet. So this is wonderful. Okay, so now I'm saying 0 is equal to, and then I'm going to put the torque from the girl here. They already gave me the force in newtons, and it looks, I'm applying this force basically right perpendicular to the beam. That's great. So when I do this, I'm doing, force times the radius. I guess I'm going to put FGG times radius times sine of theta, but that's going to be 1, plus negative times the boy's weight times radius 2. Okay, so then I could maybe I'll just move the boy's information to the right hand side, add it all. That way I don't have negatives. So I'm going to do the boy's weight times R2. Okay. So then, this is just proportional here. I've got 500 times R2, which I don't know, 350 times 1.5. Okay, so then I can divide and get this answer. Let me pause. Okay, I got 1.05. I don't know what you got, if you tried that. Okay, so that seems to make sense. We expect the heavier partner here to have to sit closer to make this balance. I don't know if you've had experience with seesaws. Okay, now the other thing I said we could solve for would be this normal force, just like we used to. Okay, because we know that the net force has to be 0. I feel like we can't both solve for that and for the weight of the beam. Maybe we have to just assume that the weight of the beam is basically negligible here. But it would be really easy to say, hey, the normal force is going to have to cancel with the 350 and the 500, so it's going to have to be 850 up. Okay, so just keep in mind, don't forget about that. that force is there, that it's important. It's just not causing torque if we're analyzing this from the perspective of the fulcrum. Okay, so that's a preview, and we will do some more examples, and you're going to try the typers for me.